So good evening everyone, and this is the lecture that we are waiting for. Series and parallel combination of capacitors is what we are supposed to discuss in this class. Series and parallel combination. I think we are done. Oh, this is not your thing. Okay, this is not your slide. Your one would be here. Yes, this one. Yes, I changed the thing. Okay, so in the previous lecture, we had started your series and parallel combination, and we had seen what happens in series and what happens in the parallel combination, how the capacitance changes when it is in series, capacitance comes down when it is in parallel, capacitance gets added up. I think we were stuck, or we were discussing the concept of battery or a cell, and we had seen what a battery or a cell does. The primary function of a battery or a cell, it is not supplying anything, it is just creating potential difference between the 2 points in a circuit, and because of this potential difference only the charges are going to flow. And we have seen that whenever we talk about charges flowing in a circuit, we are always talking about, no matter which charge is flowing, we are always talking about the flow of positive charges. Positive charges flow from higher potential to lower potential on their own. But if you want to make them flow from lower potential to higher potential, some work needs to be done, which we are also going to do. Now, who is going to do this work? Inside the battery, we had discussed what we had discussed, that inside the battery, the positive charges flow from inside the battery, they flow from lower potential to higher potential, and this needs some work to be done. And what is that work done referred to normally? I told you that word, yes or no? How do we understand that work done, or how do we understand
Automotive force, sir.
that is known as
EMF.
uh, EMF? So this work done per unit charge, this work done per unit charge in moving a charge from where to where? From the negative terminal to the positive terminal inside the battery. Inside the battery, this work done per unit charge is known as the EMF of the battery. So we have this legendary formula. The EMF of the battery is work done per unit charge. Remember, in moving a charge from the negative terminal to the positive terminal inside the battery. Do we understand this? Yes or no? No, yes. That is known as the EMF of the battery. Now you can write this formula in a different way also. Somewhere, sometimes you might be asked to find out the work done by the battery. So how do you find the work done by the battery? Work done by the battery will be charge flown through the battery, whatever charge is flown through the battery, multiplied by the EMF of the battery. Do we understand this? Yes or no? No, yes. So we can understand these two things. In this way also, work done per unit charge is known as the EMF of the battery. And to find out the work done by the battery, you always have to find out how much charge has flown through the battery and multiply it by the EMF of the battery. Do we understand this, everyone?
Yes,
Yes,
sir.
sir.
Have you noted it down?
Sir.
Okay. Now, what is the next thing that you have to understand? The next thing that you have to understand is whenever we talk about this battery, there are two types of battery that we may encounter. There are two types of battery that we may encounter. Do you know what are the two types of battery that we may encounter? The first type of battery is known as an ideal battery. Now remember, whenever we write the term ideal, Nothing is ideal in this universe, so this ideal battery is just a fictitious battery, does not really exist. Then on the other side we have the battery which really exists, and therefore it is known as the real battery. Ideal battery and a real battery. Now, what is the difference between an ideal battery and a real battery? Now, if I just try to write the first point of this ideal battery, whenever I'm going to write a battery, in most of the cases, 99% of cases, I will just draw the battery like this. I will just draw the battery like this. Whenever I'm going to draw a real battery, I am going to draw the battery like this. What is the difference? Huh? The EMF of this battery will be written as E. The EMF of this battery would be written as E, but there would be this small r. Do you know this symbol?
Resistance.
An ideal battery has no internal resistance.
Resistance, sir.
Yes, an ideal battery does not have any resistance, but a real battery has some small resistance. So it has a resistance as well. Do we understand this? Yes or no? An ideal
Yes,
battery has no resistance. A real battery has some resistance. We understand this?
yes, sir.
Now, whenever we talk about this EMF, there are two terms that we use. This is V. What is this V? This V is the potential difference across the battery. This V is the potential difference across the battery. For real batteries, V in open circuit is same as the EMF of the battery E. What do you mean by open circuit? Uh, by open circuit, I had a battery. Well, that battery is gone. Yeah? Where is my battery? Here. Open circuit means this. This battery is not connected to anything. This is an open circuit. Nothing happens. This is an open circuit battery. Now, when the battery is an open circuit, it is not connected to anything. This V, which is the potential drop across the battery, is equal to the EMF of the battery. What about this real battery? This V in open circuit is again always equal to E, which is the EMF of the battery. Instead of writing it as E, I can write the EMF. I hope you are able to understand this and are not getting confused. Yes or no? Are you able to understand this, or this is going above our head saying bye bye? First understand, then you write. Don't write. First try to understand, then I'll give you time 5 minutes, then you can write. We understand this? Yes or no? The next point, that is V in closed circuit. The circuit is closed when current is flowing, is again equal to the EMF of the battery. Why this V in both cases is same? Because there is no internal resistance of this battery. There is no internal resistance of this battery. But here V in closed circuit, when the battery is working, means there is a battery inside this phone which is working. In closed circuits, V is not equal to the EMF. Do we understand this? Now, the question comes, if it is not equal to EMF, then will it be less than EMF or will it be more than EMF? Will it be less than EMF or will it be more than EMF? V is less than EMF when the battery is getting discharged. Let me lose this. When the battery is getting discharged, then V is less than your EMF. V is greater than the EMF of the battery when it is getting what? Charged.
Charged.
When it's getting charged. So this V can be greater than or less than EMF depending on when it is getting charged or when it is getting discharged. What do you mean by battery getting discharged and what do you mean by battery getting charged? This is the positive terminal and this is the negative terminal. If the charges, when I say charges, positive charges are flowing like this. The positive charges are flowing like this. That means inside the battery, they are flowing from negative terminal to the positive terminal. That means the battery is doing work. That time the battery is getting discharged. Are you getting my point or everyone is getting confused? This is what we call discharging of a battery. Then what is charging of the battery? In charging of the battery, the reverse process happens. This is the positive terminal and this is the negative terminal. Normally, positive charge should go from the positive to the negative outside. But here, positive charges flow like this. That means the battery is getting discharged. Do we understand this? Or this has gone above our head saying bye-bye? This is what we call charging of the battery. Charges flow in the opposite direction and that is how the battery gets charged. So in this phone of mine, right now, positive charges are moving from negative terminal to the positive terminal inside the battery. When I put this on a charge, like my laptop is on charge, it has a DC battery. The positive charges will be moving from positive terminal to negative terminal inside the battery. Do we understand this? Yes or no?
Yes, sir.
This is what you mean by charging and discharging. Anyone got this? You want to
Yes,
note
sir.
it down? Have you noted it down?
Yes, sir.
Yes,
Okay.
sir.
So this is what you understand by charging and discharging. I will give you again discharging. When the battery is getting discharged, and I'm talking about this is the diagram that you will get. Charges will flow like this. And also remember, work done by the battery is taken as positive because the battery is doing work. Discharging, this happens, then what happens in charging? Positive charges flow like this. Work is done on the battery. That means work done by the battery is negative. Can you remember this? So this battery is the gentleman or lady who is doing the entire thing in a circuit. Without this battery, nothing in the circuit will work because there will not be any potential difference to move the charges around. We understand this? Yes or no? So the most essential part of a circuit is your battery. If there is a battery, then only there is a potential difference. If there is a potential difference, then only charges can flow. When charges flow, then only things happen. If charges don't flow, things don't happen. Do we understand this?
Yes, sir.
Pakka, everyone?
Yes, sir.
Okay, I'll give you a minute. Note it down. If you have missed it, note this down. If you understand this, then the rest of the part, this is the most confusing thing. I mean, if you understand this, work done when it is positive, when it is negative, because that is the case where most of you will get confused and might make a mistake. A mistake of a positive and a negative answer is the mistake between +4 and -5. So remember this and keep it in your head always. If you are done, let me know. I can move ahead in life.
Done, sir.
Girls, done? Written this down.
Yes, sir.
So in most cases, what we are going to encounter would be real battery, would be ideal batteries in question, but there could be real batteries. Whenever you see a resistance, with a battery, that means that battery becomes real and it is not ideal. Okay. Chalo, on that note, we can move ahead. The point of contention here was to get into series parallel combination, but then I did this because I just used the term battery, and I thought that if I use the term, it would be important that you understand the term, and then we will move ahead. Okay, that takes me, oops, what has happened here? That takes me to the part where we move ahead. And how do we move ahead? Okay, series and parallel combination. We have seen what happens in series combination, what happens in parallel combination. Now, what type of question are we expecting in this series parallel? The first category of question is where we are supposed to find out the equivalent capacitance. That is the first question that could be asked. Then there are questions, what will be the charge coming on this capacitors and this and that and energy and all that. Let us first tackle the first type of problem. And the first type of problems are based on what we call equivalent capacitance. Equivalent capacitance. Problems on equivalent capacitance. You must have seen this equivalent capacitance, yes or no? Problems based on equivalent capacitance. Seen anywhere? Yes or no? No answers. Have you heard this term anywhere? Equivalent, find out the equivalent capacitance, equivalent resistance. Have you heard it term somewhere, anywhere? Nowhere.
No, sir.
Okay. कोई बात नहीं. We move ahead. We have heard this term or not. We will move ahead. Now, before going on to this concept of equivalent capacitance, there is something that would come here, and we would first discuss it as well. The thing that is going to come many times would be something known as the balanced Wheatstone bridge. Heard about this name? Have you heard about this term, balanced Wheatstone bridge? A balanced Wheatstone bridge. A Wheatstone bridge is a combination of 5 capacitors. And usually these 5 capacitors are connected between the points A and B like this. Now any 5 capacitors connected like this is a Wheatstone bridge. The Wheatstone bridge becomes balanced if I call this capacitor as C1, C2, this as C3, this as C4, and this as C5. If I have 5 capacitors connected like this, it becomes very difficult to solve and find the effective capacitance or equivalent capacitance in this case, because it is difficult to understand which are in series and which capacitors are in parallel. But if there is a condition given, and the condition is you can find the ratio of C1 by C2, and if it is coming equal as the ratio of C3 by C4, if that becomes the case, then this question becomes very simple to do, because then this point C and this point D, potentially they become same. The potential of point C and point D, it actually becomes same. Now when the potential of this point C and D becomes same, then this question can be easily solved. We can understand which capacitors are in parallel and which capacitors are in series. So you can do it this way. You can see if this C and D come to the same potential, what happens? You can just neglect this capacitance 5, which is coming in between. Now, if you can neglect this capacitance C5, which is coming in between, you can now see that the C1 and this C3 capacitor will come in series. Do we understand this?
Yes, sir.
And this C2 and C4 capacitor will come in series. Yes or no?
Sir.
You can find out the series combination of C1 and C3, C2 and C4, and then you will have two capacitors which will be coming in parallel. So this, then the effective one will be coming in parallel. So you can solve the question in this way. Do we understand this?
Yes, sir.
There is another way of solving this question though. If I even redraw the circuit, and if I redraw the circuit like this, again between the points A and B, C1, C2, C3, C4 and C5, again under the condition that C1 by C2 is equal to C2, C3 by C4, again you can see that this point C and this point D have the same potential. If they have the same potential, then I can take it in this way. This C1 and C2 will come in parallel, because one plate is connected to point A and the other plates are connected to point C. So C1 and C2 can be taken in parallel. Similarly, C3 and C4 can be taken in parallel. Remember, the C5 capacitor is already out of the circuit. So C1 and C2 can be taken in parallel. C3 and C4 can be taken in parallel, and then the effective capacitance of these two will be in series, and that will help us in solving any questions on these five capacitors if they form a balanced Wheatstone bridge. If they do not form a balanced Wheatstone bridge, then the question will be solved in a different way. So this is one trick that you must remember whenever you are tackling any question on the equivalent capacitance. Everyone noted this down? Yes or no?
Answer.
Okay, great. Then I asked you to bring your that SC Verma. Have you brought it? Eh? Yes or no? No one brought it. Well done.
Yes, sir.
You have brought it. Good. Then you can move on to, I think, page number 148 of your book. I don't know, a new book or old book, and you will find this question so that you can do it faster and you don't have to draw the diagram. You can find this question. This is example number 31.5. Example number 31.5. So if you can't find it from the page number, you can find it out from the question number. This is a very simple question where they're asking us to find out the equivalent capacitance between point P and point N. How do you get the equivalent capacitance between point P and N? I'll give you 2 minutes. Think about it. How did we get 15? Now look at point P, look at point N. As soon as you look at point P and N, you can see this 10 and this 20 are in parallel. 10, 20 in parallel becomes 30. Now you can replace this 10 and 20 by a single capacitor, which is 30. 30 like this. Now, as soon as you replace 10 and 20 by 30, now you can see this 30 and this 30 come in series. 30 and 30 in series. The effective capacitance becomes 15 microfarad. Do we understand this?
Yes, sir.
Everyone understands this? Okay. Then the next one, again, scrolling down the book, and where is the next one? The next one, I think. Okay, let me take it from here. Let me take it from here. Yes. Tell me what is the answer for this one? Effective capacitance between P and Q.
Show the previous slide.
Previous slide is gone. What do you have to see? You have the book now. You can see it from the book. 31.5 beta. You do not understand the problem? Take so much of time, I will not be able to do as many questions, beta. Okay. See it. Let me know once you are done.
8/5, sir.
And this is the next problem.
8/5, sir.
How did you get 8 by 5?
First parallel, sir.
These two are in parallel. 4 and 4 in parallel becomes 2. So basically you can replace this 2
NEET, sir.
and this 2, 4 and 2 are in series. You can easily find out the relation between them. Yes or no? So as you can see, they are pretty simple stuff. If you understand them, you should be able to solve them. Okay, this is the next one. What is
Sir.
that? What is the effective? Yes. What happened?
Sir, first parallel now, sir. Pink is parallel, right, sir?
What beta? I don't understand what you're saying. You have not understood what
Sir,
is what has
the
happened
color
here?
you marked is parallel, right, sir?
Right. Oh, 4 and 4 are in parallel, so it will become 8. Sorry. That is what you wanted to find out?
Yes,
8.
sir.
4, 8 and 8. 4, 8 and 4 are in series. Thanks for correction. Got it? Have you understood this? I made a mistake. I just
Yes,
added
sir.
them in series. Okay. The next one is this. Find the effective capacitance between P and Q. Two minutes. So how are you supposed to do this? You can easily see that this 2 and this 3 are in parallel. So you can remove it and simply put one capacitor of 5 microfarad here. And once you understand, now these 3 will be in series, same charge will flow. 12, 5 and 20 are in series. You can find the equivalent capacitance. 1 by C equivalent will be equal to 1 by 12 plus 1 by 5 plus 1 by 20. You could do it this way, or you could do it in a different way. You can look at this 5 and 20. First, you can find the effective capacitance of 5 and 20. 5 into 20 divided by 5 plus 20, you will get 4. Then once you get this 4, you can find out the equivalent capacitance between 4 and 12. 4 into 12 divided by 4 plus 12, you will get 3. No matter how you do it, you will always end up with the same answer. Do we understand this? Yes or no?
Yes, sir.
Okay. Now this one. This is S.C. Verma. Question number 3. Page number 156. So if you have the book, you can just look through the book and just solve it here. You have to find out the equivalent capacitance between A and B. This is example number 3, problem number 3, page number 156. So you will save some time in drawing. You don't have to draw it. You can just see it from there and tell me the answer. I'll give you 2 minutes.
Yes,
Yes, sir.
sir.
It's very simple. This 12 and this 6 are in series. 12 in 6 series, you will get 4. Then this 4 and this 2 are in parallel. So the answer would be straight away 4 plus 2, 6. That is the answer. Great. Now this is question number 4. Same page, I think. You have to find the effective capacitance between A and B. 6? How did you get 6? No.
Sir.
You have to find the capacitance between point A and point B. So what I normally do, I give
8,
it.
sir.
I give it a tail. So now you see this 6, and this 6, same charge is going to flow through them. So these 3 are in series. 6, 6, 6 are in series. 3 6s are in series. So it will become 6 by 3, 2. So now you can take this off and just put another capacitor whose capacitance is 2. Now you can see this 2 and this 6 are in parallel. So your effective answer becomes 8. We understand this? Yes or no?
Yes,
No,
sir.
sir.
Great.
No, sir.
We don't understand this. What we don't understand? All the 3 6 microfarad are in series. We don't understand this better. Same charge flows through them. What is the confusion? All these 3 green, they are in series. What is the confusion there? Tell me better.
Understood, sir.
Okay. This is page number 164, question number 4. Question number 4, page number 164. This is the point A, this is the point B. You have to find out the equivalent capacitance.
Option B, sir.
Option B, sir. How did you get it, sir? How did you get it? That is correct. Answer is correct. How did you get it? Now see, what do we see here? This point and this point are actually connected to point B. So basically what is happening here is both the plates of the capacitor, whether it is this plate, plate number 1, or whether it is this plate, plate number 2, plate number 1 and plate number 2 are effectively connected to each other. Now when this happens, when both the plates of the capacitor are connected to each other, the potential difference between the capacitor plates becomes 0. Now if the potential difference between the capacitor plates becomes 0, there will be no charge coming on this capacitor. So you actually can take this capacitor out because this capacitor does not exist. No charge flows. Now if you understand that this capacitor, we call it shorting of the capacitor. We understand that this capacitor gets shorted, then you have only 2 capacitors, C and C, across A and B. This C and this C are connected in parallel. and therefore your answer is 2C. Do we understand this?
Yes, sir.
Great.
Yes, sir.
Chalo. Next one, this is unsolved question number 9, part 1. This C1 is 4 microfarad. The C2 is 6 microfarad. You define the effective capacitance between A and B. Question number 9 this is. Page number 165.
Sir.
Yes.
5, sir.
5, sir. 5.
How did you get 5, sir? There is a wire connected between these 2 points. So basically these 2 points do not remain different point, they become the same point. Now when they become the same point, you look at this capacitor and you look at this capacitor. One of the plates of this capacitor is connected to point A here. The other plates of this capacitor is connected to each other. That means these 2 capacitors now come in parallel. So 4 plus 6, this combination gives me 10. Similarly, 4 plus 6, this combination also gives me 10. This 10 and 10 are in series. 10 and 10 in series become 5, and that is the answer that we are looking at. 10 plus 10 in series, we will have 5. Do we understand this?
Yes,
It
sir.
has gone above our head saying bye bye.
Understood, sir.
And this is the cousin brother of the same question. C1 is 4, C2 is 6. What is the answer for this one?
10, sir.
How it is 10, sir? This entire one thing is one of this. So this entire one thing is 5. Then this entire thing is another one of this, 5. This is A and this is B. Now this 5 and 5 are in parallel. So the answer is 10. Do we understand this or bye-bye?
Understood, sir.
Understood, sir.
Pakka?
Yes, sir.
Sir.
Huh? What is happening? This one, sir. Between A and B, sir. Remember, sir, point A is here, point B is here, sir. I always put a tail so that I understand between these 2 points I have to find out. And I do not make a mistake. Yes? Any hope of getting an answer?
5, sir. 5.
5, sir. Everyone got the answer, sir?
Yes, sir.
How did you get it, sir? It is very simple, sir.
Sir.
What, sir? This, sir, and this, sir, are in series, sir.
Sir.
2, sir. Then this, sir, and this, sir, are in parallel, sir. 5, sir. Answer is 5, sir. Yes, sir, or no, sir?
Yes, sir.
This one. Now, all these questions are of a similar structure, and if you understand that structure, you would be able to solve a lot of questions on this. This is point A, this is point B. We Do we understand this, sir? Huh? I call it the series parallel, sir. See, you start from here. These 2 are in
Series.
6 and 6 in series becomes 3. Then that 3 and this 3 are in
Parallel.
3 plus 3 becomes 6.
6.
Then that 6 and this 6 come in
Series.
6 plus 6 again becomes 3. Yes or no?
Yes, sir.
And that 3 and this 2 comes in parallel. So first we have series, then parallel, then series, then parallel. I call it series, parallel, series, parallel, series. So answer here is, in this case, is going to be 5. Do we understand this, or this has gone above it saying bye-bye?
Understood, sir.
Last one, just to make you understand that.
Sir.
Yes?
Can you please explain it once again?
The two greens are in series. When you add those two in series, you will get 3. 3 and 3 are in parallel. So after one series, you have parallel. Then again you will have series. Then again you will have parallel. And that is how the chain goes on. Series, parallel, series, parallel, series, parallel. Do you understand this?
Yes, sir.
No, sir.
Try this one and probably that will make more sense. This one. You have to find the effective capacitance between A and B. Now, understand it and you will be able to do it. So how are you going to do this? These 3 are in
Series.
999 in series. What will you get? 3 9s are in series. What will you get? 9 by 3, which is 3. Then
Answer is 3, sir.
that 3 and then this 6. This
Final
will
answer is 3, sir.
this will be 3 microfarad. 3 9s in series will be 3. Then this 6 and 3 will again come in parallel. 6 plus 3 becomes
We got the
9.
answer, sir.
Then
Yes,
this
sir.
9 and 9 and 9 again come in series.
Series.
9 and 9 and 9 becomes 3 again.
3.
Then this 3 and then
6.
6 again come in parallel.
9.
Again 9. Series, parallel, series, parallel. Then this 9, this 9, this 9 are in
3.
series.
3.
Series, parallel, series, parallel, series, parallel, and so on. Do we understand this?
Yes, sir.
So, you have questions in your book, SCV. The questions may be of capacitance or the question may be of resistance. They are done in similar way. So, you bring your book tomorrow. Today we have done it for capacitance. Tomorrow we'll do more questions on capacitance as well as we'll take out resistance as well, because there is no difference between series and parallel combination. If it is in series and capacitance, you put in place of capacitance, you put a resistor, still remains in series and resistor. It does not change to parallel. The only thing is the way you add them, that changes. So we will see that way when we come in the next class tomorrow. Be prepared with your books. Why I'm asking you to bring your book? So that you can do a lot of questions. Because if you draw each and every diagram, it will take a lot of time to draw the diagram, and then we don't have that much of time. So we'll
Yes,
meet in the next class and we'll try to do more questions. Take care. God bless all of you. Bye bye.
Thank you, sir. Bye, sir.